Who we are and what are we doing here? What's the class name? Physical chemistry. But in fact, we are doing quantum, which is a natural part of the physical chemistry. So, what are our objectives or objectives? How to pronounce correctly? Just help me. Objectives or objectives?
Objectives.
Objectives. Okay. What are they?
Understand duality.
Oh well, duality, causality. We all heard, but what from more mathematical, rigorous way to get basic principles and convert ideas into language of math, so that we can explain more practical examples. On your language, duality of what?
Wave and particle.
Wave and particle of what?
Electron.
Yes, of electron. So we do not care about light, we don't care about photons for a time. Maybe by the end of the course we can tell something like photochemistry. Or there is a new area in experimental chemistry, microwave chemistry. When you take your container with reaction, just put in microwave. Really, there are a lot of discoveries and publications. It changes how the reaction is going on. Even if you do not bring it to boiling, microwave changes it, and one doesn't need specific equipment. Okay, principles for electron motion, because electron is so energetic that it doesn't want to stay still. Waves, which can be traveling and standing, right? I do not have pedagogical talent to ask the question correctly. Standing and traveling can be what? Waves. We got an equation that generates traveling and standing waves. Hopefully. So if you take an f function, apply second derivative over space and over time, and function should depend on at least these two variables. Put somewhere 1 over velocity of this wave, then such equation is expected to generate waves. In simplest way, infinite cosine, in generally some traveling waves, wave packets, and we are potentially able to deal with math that is responsible for wavy motion. I wasn't lying, but probably I broke your expectations. This equation, wave equation, has nothing to do with electron. This equation is good to describe electromagnetic waves or guitar strings or like drums surface, but not electrons. If you want an equation for electron, it should be not second derivative over time, but first. And there are reasons for this. But to come to this ultimate truth, we will spend a little bit more time. Which movies did you watch? No, not general. I know most of you watched next episode of GOT, but which movies did you watch in class before we wished each other a nice weekend?
Of the orbitals?
Yes. So what do you remember from these movies?
Full numbers give you nice round circular orbitals, while if you had like a partial orbital, it starts getting funky.
Yes, excellent. So these images were a rough visualization of the Bohr's orbitals, which were like breakthrough at the beginning of 20th century for explaining atomic spectra. So there was a thought that it is a planetary type motion, like electron like a planet circling around nuclei, but it can circle not at any distance and any velocity. There are specific distances and specific velocities that give discrete integer numbers of this distance times momentum, which is angular momentum, right? It is what you were always enjoying in your kindergarten, Bohr's orbital. And as, any chemist is well aware of the orbitals, right? SPD, which somehow related to this. But we want to grow as intellectual elite of the planet. We want not just absorb blind information as a disk drive and then reproduce it. We want to develop our own ideas and connections between pieces of information, being able to generate new information. So what are the principles? What do we learn from this Bohr model and this movie? So something wavy is going in circles, and this something is happy to make discrete number of oscillations. Please object if you do not like this verbalization. Okay, no one objects, then it is ultimate truth. Democracy. But we need to get an idea what is moving, what performs these oscillations, and then later how to develop mathematical tools to describe it and project it on something more complicated than boring circular orbits. So we will make intellectual effort to get some more specific ideas. What is changing along Bohr's orbitals? What is oscillating? Why there are discrete numbers? And in fact, we don't care about Bohr orbitals. It is only a toy model to develop ideas. How will we get through? What are our plans for today? We will have two sections. During the first section, you can lean back, turn the lights on, take popcorn, and fall asleep. I will give you a sign when to wake up and memorize or take records. It will be a little more than necessary math, and it will be a little more than chemistry in first section. Second section, it will be boring as well, but you cannot avoid it. Second portion will be I'll try to recall what are complex numbers. If you are happy with them, complex, not like, oh, they're so complex, but it is a term. And many of you may be well aware of those, and then you can keep leaning back and sleep until the end of the meeting. But if you don't, I just quickly remind. So, two things, two chapters. First, it will be our travel into world of physics. We what is laziness? Try to give some definition, because laziness is an engine of a progress. People design new tools when they are lazy to do it by hand, right? But what is laziness? Try to work. Huh?
Wanting to spend like the least amount of energy possible.
Ah, excellent. Probably I cannot find better, but maybe other same idea but different words. Energy is too complicated, but if I lay back on couch, I do not want to do anything. Right? So I want to minimize not
Effort.
only
Effort.
minimize effort, good. What else? I just want you to design the right word. Minimize. When I do something, I perform work, yes. I act, I do action. When I do nothing, I minimize my action. So first section is least action principle, which most of us are well familiar in regular life, but it is one of the fundamental cornerstone of modern science. And there are mathematical formulations for it. You know, there was Newton with his equation of motion for any like particle or chair or wheel, right? So like, give me a sign if you do not know Newton's equation of motion. So no one gives signs, so I shouldn't show it. Acceleration equals force divided by mass, right? And if one solves it as differential equation, one can get a trajectory, a law of motion, how a particle moves. Position is function of time, right? All correct, is good. Well, respect to Newton. But it is too simplified. There are more advanced, more philosophical ways to get the same answer with more boring and complicated theory, which can be generalized to something more complicated than just set of particles. And the competitor of, so Newton was British, and his competitor is from France. So the name is Lagrange, and there is a Newtonian equation of motion and there is a Lagrangian equation of motion. Why should we dry our young brains to this new piece of information? Because we will answer our main goal for today. This will be also cornerstone to answer, get an idea what is oscillating or what is changing along the trajectory in Bohr's model. Least action principle, Lagrangian mechanics. Again, do not concentrate. We will, I promise we will never do homework based on what I'm going to say. It's only for concept. So it's completely understandable if you will be sleeping during this piece of information. Where do I go? I'm going to zoom into the screen. Okay. So this is something you remember from, you've got the general idea. Now I will be trying to give illustrations and details. You remember these movies, right? And here is the angular momentum, which is distance from center times momentum. And this stuff takes discrete values times Planck constant. It is what you learn in kindergarten when you look at Bohr's model and planetary model of atom. Oh, if it would be like freshman course, or if I would think of you not as intellectual elite, but as a kids, I would show portrait of Bohr, history which year it was developed. But let's go quicker, and you can find portrait of Bohr in. So discrete, and if it is not discrete, then something wrong is going on. So we are looking for alternative way to get answer to main question of mechanics, to find trajectory of a particle as function of time. Simplest way is to solve Newton's equation of motion, but there is an alternative way. So suppose you do have a trajectory, position as function of time. The strange symbol is t, which is like x as function of t, something moving. Then at each point of time you can find velocity as derivative of position, right? You can find kinetic energy, and you can find potential energy. Like kinetic energy can be this mass times velocity squared divided by 2, right? And potential energy, well, if it is electron, it is, let's something simple, kx squared O2 for spring and mass. It's not general, it is only one example, but you can get it. And the values of this energy will be different at each point of trajectory if there is a motion. Where do we use it? Where one can use it? One can take kinetic and potential energy as a function of time and build the total energy, T plus U, right? It is what you were doing if you were taking some physics classes or if you during your science in high school. Why don't we replace plus with the minus? Just as experiment. So T minus U and call it different letter. H for Hamiltonian and then for Newtonian mechanics and L for Lagrangian. So if you design something, just call it after your name and make others to repeat it. So there is, by the way, what is the dimensionality of this L symbol and H symbol? Dimension. Something simple. There is no trap. There is no trick in this question.
One-dimensional in this case?
No, not dimensionality. Not like 2D, 3D, but is it like
Energy?
yes, energy. Both H and L dimensions are energy. Okay, and here's the thing. If one takes the value of this L thing, L variable, at each point of time along the trajectory, and adds it together, integrates, then it will be a magic tool. It will be one number for each trajectory, but there are theorems and there is a lot of experience that only those trajectories in nature which minimize this integral are allowed to exist. It's on one hand it is observation, on the other hand there are derivations. So if you do S equals integral L dt, then one call this thing action from initial time, and only those trajectories that minimize action are observed. So whatever is moving moves according to minimal action or least action principle. So laziness in action. Good. So now you are certified experts in advanced classical mechanics. You can go to physics department and get credit. Actually, they studied for a semester. Same thing. Do not be scared. I just exercised how to type equations. So what do we get here? So along trajectory, you can get kinetic energy, you can get potential energy, you can build kinetic plus potential or the subtraction. If you build this action variable, it is a criterion. So you can build trajectory without solving any equation by random number generator. But then, if the action will be minimal, this is a correct trajectory. If it will be maximal, it is a wrong trajectory. Okay? If you're sleeping, that's fine. This is not for chemistry, and this will not affect any of our future. And here, from this least action principle, one can make an equation of motion that will be a replacement of Newtonian equation of motion, of Newton's second law. So derivative over position equals derivative over velocity is another derivative over time. and it will give the same answer for any system. And it is more general because it can be applied to something more complicated. The only thing, so if you are sleeping, you may wake up and concentrate. There is a time dimension, time and energy. So the magic thing that gives answer to any modern science is energy times time. And it will be this action that we want to minimize. Okay? There is an important observation that we can derive or just believe. So what is the dimension of the stuff that is being quantized in Bohr's model? And if we do not know the answer, we need to derive. So it is distance times momentum, which is, okay, let's write it like x times, what is momentum? Is mass times velocity. Right? So it is distance squared, mass in the first power, and we can put t squared here, but to avoid line and keep our reputation, we should put t in the first power in the denominator. So I replaced t in the denominator by t squared in the denominator, but multiplied by t. No line, all pure by now. Now, which equations from previous slide pop up in your head by looking at mass times derivative, second derivative, or first derivative of distance over time squared? You wanted to say this, right? So what is this? Energy, kinetic energy, right? So we can identify this term as energy, and this is as time. So here is something important. The dimensionality of the stuff that is being quantized in Bohr model is energy times time, which is the same dimension as action. And Planck constant also has the dimension of action. So it is not math anymore, it is now our intellectual analysis. So if we do have something that is getting quantized and it has dimensionality of action, and this something, if we divide it by Planck constant, which is also in a dimension of action, then we will get dimensionless angle, the phase. So we can think of the electron moving on the circular orbits and accumulating action from the initial to final time that we explore. So electron accumulates action. But if we divide it by Planck constant, it will be angle, it will be phase that can be fed into oscillatory function. So where are we now? What did we get? I have communicated you the main idea. Now we need to maybe verbalize it better or wrap it up. So, and you shouldn't underestimate, you are making a major effort that took 100 years for humankind right now. The rest are boring math and technical details that you can hire someone else. Now it is something that we need to think ourselves. So if a particle moves along trajectory, it accumulates action. But if you divide this action by Planck constant, it can be associated with the angle, you know, degrees or radians, that it's also accumulated during the trajectory. On another, in Bohr's model, we have this cosine oscillatory functions. And of course, oscillatory functions have argument, have an angle inside them. Why don't we hypothesize that this angle, this argument of this trigonometric function is actually action divided by Planck constant. So action that can be computed by this apparatus of classical mechanics. So during the motion you accumulate action, but if you divide it by a constant, it means during the motion you accumulate phase. Motion is accumulation of phase. And this phase is argument for some oscillatory function. Objections? Then it is ultimate truth. So, argument of Bohr's wave is action divided by Planck constant. If you object now or stay silent for until the end of the course. Are we happy? Are we done for today, or we have something else to complete? So you did a major breakthrough. It looks a little like jelly, not very solid, but it is a major idea that will help you to become excellent chemists in the future. It helps to understand stability, reactions, and what is going on the atomic level for atoms and molecules. No philosophical principles anymore, but now we need a mathematical tool. We need to be, I gave you warning, it will be warning for the rest of the lecture. Now we are done with physics and we are going into math. It is what we do in chem courses. So, when we were thinking, yeah, it's just action divided by Planck constant is something that should be integer. So when we were thinking of these movies, images, videos of the strange stuff circling around, we were thinking that a wave is a harmonic function, something oscillating, sine or cosine, trigonometric function. But is it general enough? Can we fall into trap and come into situations when these functions are not good anymore? Like interpretations of these waves, of something that moves around in the electronic wave, is to be discussed later. But there are two major interpretations. One is that it is a probability amplitude, and probability is typically between 0 and 1, positive. Another interpretation is that it is density of electrons, so number of electrons per unit volume, which also should be positive. And cosines sometimes are getting negative. So maybe we need to do something with them. Maybe it is not ideal, it's just a little bell. But if it would be cosine, we would say that electron is cosine of action divided by Planck. Do not reproduce it in public, it is wrong. We are going to be much more rigorous. Did ancient Egyptians used fractional numbers? Did they use real numbers? I don't know. Maybe they did, but for beginning of civilization, it is natural to use natural numbers, like number of apples. But if you try to divide it, and sometimes it doesn't come to natural number, and it is a push to design real numbers, which can be between 0 and 1 or between 1 and 2. By the way, did you ask Siri, what do you get if you divide 0 by 0? Try it. It is, well, I think it is not very much intelligent because it repeatedly gives the same joke, but when you hear it for the same time, you're getting impressed. Well, some of us getting impressed. So there is a.
Oh, nothing. I'm just saying the Siri thing.
What?
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 What's the answer for the Siri?
Uh-huh.
Oh, well, it says, try dividing 0 cookies among 0 friends. See, it doesn't make sense. And now Cookie Monster is sad because he doesn't have any cookies, and you're sad because you have no friends.
So you see how math is developing. But there are problems that push us from comfort zone to lack of comfort. And another push was at the time of like Renaissance, when people started making cannons and trying to predict trajectory where the projectile will fall down. There, to solve this, one needs to solve second order equations, square equations, like x squared plus x plus 1 equals 0, or with different coefficients. And sometimes, you know that you get out of your comfort zone. The solutions get into something that doesn't belong to real numbers. For some examples of the coefficients, you can get into solution which is square root of minus 1, which doesn't exist in real numbers, but probably doesn't bother you, right? So what is square root of minus 1? I. Good. So what is complex number? I is a complex number, right? So typically, when we speak about real numbers, it is one line of continuous changing the variable. But if there are complex numbers, it's like two-dimensional space with two coordinates, one for real and another for imaginary. And these complex numbers are designed to solve quadratic equations that use square root of minus 1, and we will need it because the stuff that oscillates in Bohr's model can also get complex. Okay? So if we define this I number as square root of minus 1, then you have real projection and imaginary projection. They together build like two-dimensional vector, which is a complex number. It doesn't surprise you. Good. What should we know about them? Some basic principles. You can specify complex number by real and imaginary projection, right? Real of Z and imaginary of Z. You can call it X and Y. But there is an alternative way to represent complex numbers. Which one? So this one is rectangular system of coordinates because this x and y projections are oriented by right angle, 90 degrees. So this is rectangular system of coordinates. Which other system of coordinates can be used for complex numbers?
Polar.
Yes. So what is it?
Just an angle and a distance from the origin.
Yep. Would you like to try this equipment?
Sure.
But it will save me a couple of minutes.
You just trace.
Yeah,
your
just
finger on it,
by
drop it.
fingers. Yeah.
So then that same point, that. Okay.
Escape.
How do I? Oh, just have to do that. Let's be a little faster.
Excellent. Thank you so much. So the same number, which we can call by letter z, can be specified by polar system of coordinates. So z, and now we need to establish connection between rectangular and polar representations. R is probably distance. How do you find distance in right angle triangle? I have no doubts that you know. I just write it down. You approve, right? Good. And you can call it absolute value of z. Is there a comfortable equation for this angle? Or we want to practice laziness and waste action and replace angle by something more easier? Well, there are equations, but I don't want to memorize them. One can, instead of angle, one can speak about sine and cosine of this angle. So the x will be this distance times cosine of phi, and y will be this distance times sine of phi, right? And if we are accepting the notation for complex numbers, we can take the length of this vector and for orientation use a vector that has always length 1. If you build a vector with projections sine and cosine at the same angle, you use a vector with length 1 because of sine squared plus cosine squared equals 4. Cosine phi plus I times sine phi. So at least we have a conversion from polar to rectangular system of coordinates. And so it is a mathematician, you know, Euler angles, if you do three-dimensional. But one of his great contribution to our course is equation named after him, Euler formula. Give me a sign if you hear it for the first time. Secretly, so others do not see it. Okay, give me a sign if you've heard about it before. Okay, so I'm wasting time of reminding you, but I still will because it's hard to change my plans. So what does Euler formula connect? In fact, we have written it on previous slide. So what does it establish connection with?
Complex numbers.
Huh?
Complex numbers and real numbers.
Yes. We almost have it in this line. but the Euler formula tells that if you have cosine of phi plus I sine phi, then it will be e I to the 4. So it is exponential with argument being imaginary. So argument of exponential is a complex number. And if you do it this way, if you plug this exponential there, nothing tragical is going on. It will be just x and y projections, real and imaginary part. So Euler authorizes us to use complex numbers as argument of exponentials. Euler permits complex power of exponential. Good. So it is something that we will use in the course. Please do not sleep here. Please make sure that you are okay with this equation. It is not frivolous decision to torture young brains. These equations are designed by people for people, because otherwise you will do too many mistakes in describing electrons. This idea of complex arguments of exponential is really helpful in describing wave functions, in describing electrons, in describing Bohr models and other things. So here we are coming to the very close to the end of the mumbling part of the course, where we have wavy, jelly, general ideas, and very soon we will be more rigorous, more practical. But still, at the wavy side of the course, something that oscillates in Bohr models can be thought of as periodic function. You see, due to Euler equation, exponential with imaginary power is something that oscillates in both real and imaginary parts. And the angle that is used as an argument for this exponential is action that being accumulated by an electron along the trajectory divided by Planck constant. So it is not rigorous, but is our pilot idea about what is going on along these orbitals. Electron accumulates phase, accumulates action, we divide it by constant, Planck constant, get phase, get angle, and then plug it into exponential function. So it oscillates in both real and imaginary parts. So we are going to develop math that will help us to work with functions of this type. And we will use complex numbers often, fortunately or unfortunately. Where we are. Basically, I'm done, but for the things that are related to the course. But here is the thing that you may enjoy in your everyday life. At least I enjoy. It is too much of intellectual effort for me to memorize trigonometric equations. But with help of Euler equation, you can re-derive them almost instantaneously. So we will finish as prescribed, whatever 3 minutes allow us. But if you need, for example, cosine of 2 arguments, you can build it due to Euler formula as exponential of some argument, which will be cosine imaginary sine. But on the other hand, you do know that exponential of the added arguments is a product of two exponentials with separate arguments, right? And if you use this fact, you can replace first exponential as a cosine of first function, imaginary sine of the first function, and the same thing for the second. And then this thing that was torturing me during the high school and freshman time can be redirected much easier than memorizing. So you just algebraically make equality between upper and lower lines, and as the result, you are getting trigonometric equations. Do you want to practice it now, or do you want me to practice it? I'm open. But it goes against my principles of laziness. Maybe I have a what? Cheat sheet. I did it before. Do you see it or not quite? So you write that summation of cosine of added argument, then you open brackets from 2 and 2 terms, you get 4 terms, and then you make establish equality between real part and imaginary part on the left and right sides of the equation. So then your cosine of alpha plus beta will be what is real here, first and last term. So cosine alpha, cosine beta, minus sine alpha, sine beta. And this sines and cosines just come from opening the bracket. And then that's it. You get an equation for cosine alpha plus cosine beta, which we used last time. So it kind of loops between lectures. So what did we got today, and where are we going next time? It is too early for any homework or labs. We need to talk a little bit more about general principles. But now we are coming to the level where we can think more rigorously of motion of electrons. We've got least action principle, and we got our main hypothesis. Well, it is not ours because it was designed by other people like 100 years ago, but we got a hypothesis that electron accumulates action along its trajectory, and this action is used as a phase of some oscillatory function. The interpretation of this function, what is oscillating, is yet beyond our discussion, although later we will learn that it is either probability or electron density, if you take it squared. And to treat it more rigorously, we need complex numbers, because this something can be either real, imaginary, or summation of those. How would you formulate the goal for our next meeting? What would you like to learn if you still need to learn something? Analog of wave equation, but for electrons. Okay? Meeting is done. Thank you for staying. See you on Wednesday, 11th.